Okay, so today I'm going to be covering Prim's algorithm. So Prim's algorithm is a greedy algorithm which finds the minimum spanning tree of any connected graph. And so when you have Prim's and there's the other algorithm Kruskal's, and they're usually taught in tandem to each other. With Kruskal's, you are picking any edge in the graph, and it does not matter if it is connected to any other edge that you've already picked. So for instance, with Kruskal's, we could pick this edge BC and then pick this edge EF. And it doesn't matter if they're connected or not. But with Prims, it does matter. So with Prims, we're going to only consider edges that are connected to nodes which we have already used. And another common misconception with Prim's algorithm is it has to follow sort of a straight path. So for instance, if you start at A and you go to B, well then you can only consider C and F. And this is not true. If you have A and B, you can also consider E because it's connected to a node that we've already used. And we'll see this and this will come up as we go through the algorithm. But if we run through prims and we suppose that we start at A, I'm just going to add A to our used edges here. And I'm going to use this notation. And this notation means we go to A from this node with this weight. And because we're starting at A, we're not going to A from anything, so we're just going to put a dash. And because it has no weight, we're also just going to put a dash. So we're going to start at A. And what we're going to do is we're going to look at every other node in the graph. So let's start with B. We're going to go to B from A, and we can see that has a weight of 3. So again, that's what the notation means, going to B from A with a weight of 3. And now if we look at C, what we see is that we actually can't get to C from A at all. And so the way we're going to mark that is we're going to put a dash because nothing that we currently have can go to C. And the weight we're going to put as infinity. And so now let's look at D. And with D, we have the same thing. We cannot get to it from A, so we put dash and infinity. And now let's look at E. So we go to E from A, and we can see we can, and the weight is 6. And now the final node is F. Go to F from A with a weight of 5. And so now that we've looked at every node, what we're going to do is we're going to look through them and say, okay, which one has the least weight? And here we can see it is B. So B has a weight of 3, which is less than all of these. And that really is the reason why we fill these in with infinities. Because when you're running through the algorithm, or when a computer is running through the algorithm, you need to do a comparison and you need to find the least thing. And obviously, if these are infinity, then, you know, everything's going to be less than that, so you're not even going to consider it. So here we have B. So I'm just going to mark this edge in blue to say this is the edge we took, and I'm going to mark these nodes to say that we've been there. And I'm also going to add this edge at the bottom. So we went to B from A with a weight of 3. And so now we're just going to go through the same process, except now we have these 2 nodes to consider. So now when we look at C, we're no longer going to say we can't get to C, because now we can consider B, and we have this edge here. So we're going to say going to C from B has a weight of 1. And now we can look at D, and we can see, okay, even with B, we still have no way of getting to D. So we're going to stick with the notation, And now we're going to look at E. And we're going to say, okay, well, we're looking at E, and even though we have B here, it doesn't actually help us at all. So the edge is the same as before. Going to E from A with a weight of 6. Now we can look at F. And so now when we look at F, now that we're considering A and B, before our best path was this edge, AF with weight of 5. But now that we have B, we actually have a shorter edge of 4. So we're going to say we're going to go to F from B this time with a weight of 4. And now that we've listed every node and how to get to it, we're just going to do the same thing. We're going to look at the minimum weight and we're going to say it's C with a weight of 1. And I will mark that we went there. I will mark this as visited, and I will add it here to our list of edges for the minimal spanning tree. And now we're going to repeat the same process, except now we have 3 nodes to consider. So now when we look at D, we actually have a way to get there now through C. So now we can say we go to D from C with a weight of 6. And now we can look at E, and we can see that C does not actually help us here. And so we're going to go to E from A with a weight of 6. And now we can look at F. And here we can see that there's actually a tie here. There are 2 smallest from B and from C. And the way we're going to break the ties, any tie that we come across, is just by doing it alphabetically. So I'm going to give the priority to B because that comes first. And so we're going to go to F from B with a weight of 4. And so this is all of our nodes. And we can see that the least is F from B. So I'm going to mark this. Mark F as visited. And I will add this down here. And now we move on. And now we have 4 nodes to consider. So now we look at D, and we can say, okay, there actually is a new minimum going from F. So we go to D from F with a weight of 5. And the only other node we have to consider here is E, which actually does have a new minimum of 2. So we go to E from F with a weight of 2. And as we can see from here, the minimum is E, F, this edge. So we're going to mark that and mark E as visited. And we're going to put it down here in our edges. And now we only have one more edge to look at. We have this D node, and we can see that the minimum going to D is from F with a weight of 5. And we can mark that off on the graph. Mark D as visited. And finally, we can put it down here with our edges. And so this is Prim's algorithm to find the minimum spanning tree, and this is what it looks like with all the blue edges. And then here we list the entire path, all the edges, and yeah, that is how you apply Prim's algorithm to find a minimal spanning tree.